Here are solutions to homework set number 9 for ECE 376. In this homework, we're looking at interrupts, specifically timer 0, 1, 2, and 3 timer interrupts. Now with timer interrupts, I can measure time, 200 nanoseconds, which is kind of impressive. So with that, I can see how long it takes to execute some code. So for example, if I have the following code that's using integer addition and multiplication, how long does that take to execute? The trick here is to set up a timer interrupt. Here I've got a timer 0 interrupt. All it does is keep track of time. Every 65,000 clocks it wraps around and increments time. And the main routine, I can now use that. If I record that counter time plus timer 0, put the two together, I've got a 32-bit time with a resolution of 1 clock, 100 nanoseconds. So to see how long something takes, I'll record the time before the event, do something, record the time afterwards. The difference in time is how long it took to execute. So, if I stick this in the middle and measure the time before, time after, take the difference, I get how long it takes to do 3 integer adds, 2 integer multiplies. And the answer is 197 clocks, or 19.7 microseconds. Floating point operations do the same thing with 3 floating point numbers. That takes 3,409 clocks, or 340 microseconds. You can notice that floating point is much harder than integer math. This is a processor that only has addition, subtraction, times 2 divided by 2. You can do floating point numbers, but it takes a lot of instructions. 3,409 in this case. Third, let's set it up so I hit the button 10 times, then release. So that's kind of what this code has. I wait for you to hit the button, record that time, hit the button 0 10 times, bump, 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 bump. When I'm done, record the time after 10 button pushes, display it. And again, when I ran it, it took 911 milliseconds. Every time you run it, you get a different answer. But anyway, that's measuring time 200 nanoseconds, something you can do with timer 0 interrupt. Problem 2 is output 4 different frequencies at the same time. To do that, I use 4 different timer interrupts. The interrupts do not conflict with each other. They both run at their own merry way. Every n clocks, each one interrupts. And with the code, I'm just going to toggle a pin. Like down here, every interrupt, I toggle a pin. To set the frequency, if I want to output 87 Hertz, I want to interrupt every n clocks, where n is 10 million over 2 times Hertz. If I calculate that, I want to interrupt every 57,000 clocks, 51,000 clocks, 45,000 clocks, 40,000 clocks. To do a timer 2 interrupt, I've got to come up with A times B times C that's close to 45,000. And this combination works. There's other combinations. For timer 0, 1, and 3, it's actually a lot easier. If I set the prescaler to 1, that's how many clocks between interrupts. As long as this is less than 65,000, I can just use a prescaler of 1. So in the code, what I'm going to do is, this is timer 0, interrupt every 57,000 clocks. Timer 1, every 51,000, every 40,000. This number right here is kind of an offset. That's kind of fine by trial and error. If I do this, the clocks are a little bit off. That's because it takes a few clocks to halt the main routine, jump inside the interrupt service routine, get to this line of code. By trial and error, that was about 25 clocks. As I move down in the code, it takes longer and longer. That was about 32 clocks, about 41 clocks. If I bias that correctly, I should get the frequency dead on. So at 87 Hertz, I was pretty close. That's this number here. When I'm done, these are the actual frequencies. Pretty darn close. That's the beauty of timer interrupts. I can output a precise frequency, and I don't have to use trial and error, guess again. I can calculate how many clocks between interrupts and just plug in that number. Want a different frequency? Just change that guy. Problem 3. Okay, in this third one, I want to output a 3-phase sine wave. That's something that you need to drive 3-phase AC synchronous motors. So how do I do that? Well, I'm going to use 4 different interrupts. Timer 2 just keeps track of time in milliseconds. Timer 0, 1, and 3 generate the pulses. So what's going to happen is on timer 0, or timer 2 I mean, timer 2 kicks in every millisecond, gives you 1 kilohertz. It always sets the pin. I also set up in the future like a timer 0 interrupt that clears it. If I change the number of clocks between when timer 2 is triggered and when timer 0 is triggered, I can change this duration, change the pulse width. Change it between 1% and 99%. So what I'm going to do is use a bunch of interrupts. Again, timer 2 sets the pins and then sets up the timer interrupts to clear them, then exits. A little while later, the timer interrupts kick in, they clear it, and the main routine just keeps on iterating and setting the pulse widths. And what I want is the pulse width, like for A, to go from 0 to 100%, back to 0, and pause. 0 to 100%, back to 0, and pause. Repeat every 3 seconds, or 3,000 milliseconds. So that's the idea. What the code looks like. In terms of the interrupt service routine, timer 2 does the work. As I set RC0, 1, and 2, I set up timer 0, 1, and 3 for n clocks in the future, and increment time. Just to make life easier for the main routine, I also keep wrapping around. If I go past 3,000 interrupts or 3 seconds, go back to 0. So time is just going 0 to 3 seconds, 0 to 3 seconds, 0 to 3 seconds. The main routine is going to use that to output your waveforms. So as you go from 0 to 3 seconds, that's what I want for phase A. In addition, this right here is I have problems at 0. If it's 0 duty cycle, I just leave the pins cleared. That's kind of one way to handle 0. You typically have problems at 0 and 100%. This is kind of how I handle 0. I could do an if statement up here. Don't clear if I'm at 100%, but I didn't do that. Anyway, that's the interrupt service routine. To check that out, let's write a test code. That's typical in programming. I want to write a test routine. If I set the pulse width to 1,000, 2,500, 8,000, 1 millisecond is 10,000 clocks. If I set these, what I should see is 10%, 25%, 80%. So running that code, notice the pins that's your 10%, 25%, 80% on. If I measure the voltage, 10% of 5 volts is 0.5. Ish. If we go to 25% of 5, that's 1.25 volts. If I go to 80%, that's 4 volts. Should actually be dead on. My 5 volts is a little bit off. But anyway, that's my pulse widths. So at that point, I'm fairly confident that this routine's working. So now, if I change NA, NB, and C to do this, I should get my half-rectified sine waves. A couple ways to do that. One is I could do a parabolic curve fit. I've got these 2 points at 0, halfway through, 1500. I want to generate a parabola where the peak is, say, 9800. One way to do that is, if this is t, I'll have t times 1500 minus t gives you a parabola times a constant. At the midpoint, I want the product to be 9800. Problem with that is 750 squared. The midpoint is kind of large. So what I did is I divided by 10. So when I divide by 10, it just goes 0 to 150. That's this guy. At the midpoint, I'm at 75. 75 squared times k should be 9600. That's where I got the 1.6. Something that gets you close to like 98%, 99% duty cycle at the midpoint. So that's phase A. That's going to go from 0 up to here. If it is beyond 150, just output 0. Phase B is the same thing, just shifted by 120 degrees. The period is 3,000 counts. Or divide by 10, 300. Shifted by 300. and same operation. Phase C is shifted by, there's one right there, shifted by 200 to 40 degrees. Same calculations. That's one way to do it. Second way, what a lot of people did in the homework, is use a table. In MATLAB, I can generate a table to generate the sine wave, half-rectified sine wave. I'm going to go from 0 to 99%, back down to 0, and pick the period. I chose 30 points for my lookup table. So here's 30 points. This is a sine wave, periodic in 30 points. Clip it, makes that half-rectified sine wave, and scale it by 98,900, convert to an integer. When I do that, this is y. That's my table values. And that's my little stir step. As I go through the table, I can sit there and have it get brighter, get dimmer, and turn off. The main routine then would just be, I've got time running in the background. That's from timer 2, 0 to 3000. Take that times 0.01, 0 to 30, mod 30. There's my 0 to 29. That's my pointer to lookup table. For phase A, I just use the pointer directly. Phase B, I shift it by 120 degrees, or 10 counts since the table's 30 long, 1/3 of the table. Phase C, I shift it by 2/3 of the table. And again, it's going to get brighter and dimmer, brighter and dimmer. Download that code, and you can see it running. So this is your phase A. If you look at the LEDs, A gets bright, then dim, bright, then dim, bright, then dim. Keeps repeating. Look at the voltage. It's going to go from 0 to 5 volts back to 0, 0 to 5 to 0. That's your half-rectified sine wave. Each of these is 120 degrees out of phase. So with that, I can now drive a 3-phase AC synchronous motor, or BLDC motor. All with timer interrupts. One third comment is I could use the table a little bit more accurately. What I'm currently doing is I just look at the current output of the table and just spit it out for, in this case, 100 counts, 100 milliseconds. If I were to use interpolation, I'd get the red line and get a more accurate waveform. With interpolation, I could just use a subroutine. I know the current time, 0 to 3000, and it's going to sit there and say, here's the current point, there's the next point, I'm right here. Interpolate as I go from the first one to the second, do a straight line curve fit. Takes more computations because this is using a floating point multiply, actually 2 floating point multiplies, and 2 modulus commands. So it takes a little bit longer, but you get a better waveform. One last comment is mod 30 is really inefficient. If I were to do a power of 2, like mod 32, it'd be a whole lot better. Instead of divide by 100, make that divide by a power 2. That's much more efficient. If I modified this so everything's a power 2, it would run much faster. So that's really what you prefer doing in practice. For the homework set, so this is what the 3-phase sine wave looks like when you put it on the oscilloscope. I've got the pulse width modulation for phase A and B. It's only a 2-channel scope, so I can't really show you all 3 channels. But you can see the pulse width getting wider, shorter. That's mapping out the sine wave. Now if you want to see the actual sine waves, I just took the PWM outputs and ran them through a low-pass filter. So that's a single-stage RC low-pass filter with a corner at 10 readings per second. Kind of an overkill, but it's what I had on hand. So with the PWM filtered, here's what you see. That's the half-rectified sine wave on 2 channels. Each one's 120 degrees out of phase. Get my mouse back. I would just stick with these numbers. So that's homework set number 9 for 376.